The motivation for this project is to demonstrate the principle of Newton's second law of motion, which gives the relationship between the net force, acceleration, and mass. The equation used to quantitatively visualize the application of Newton's second law is the following. A equals F net over m, where A is the acceleration, F net is the net force, and m is the mass of the object. Our goal is to determine if an object with greater mass will experience a smaller acceleration and net force than an object with a lighter mass, because acceleration and net force are inversely proportional to mass. We also seek to confirm the presence of unbalanced forces that causes objects to accelerate with an acceleration that is directly proportional to the net force and inversely proportional to the mass. The physics concept used in this experiment was the principle of Newton's second law of motion, which gives the relationship between the net force, acceleration, and mass of an object. The slope of the velocity versus time graph will be used to find the acceleration, which is the rate of change of velocity divided by the change in time. Even more, the graph will reveal an initial segment with a constant positive acceleration, a middle segment with zero acceleration, and a final segment of constant negative acceleration. Furthermore, the force of each object will be compared using the following calculation: f of x equals g sine theta, after acceleration has been calculated. The final velocity, which is equal to the acceleration, was found with v equals the square root of 2gh. The resulting predicted and observed forces were compared and analyzed. For our predictions, we believe that the heavier car would have a lower acceleration and incline force higher than the lighter car. And we also hypothesized that the free fall is not in effect due to the inclined plane. In terms of our observations, we saw that the heavier car had the same acceleration as the lighter car, and that the heavier car had a greater inclined force than the lighter car. In both cases, mass is negligible, free fall is not in effect, and the angle impacts the final velocity, and therefore the acceleration. For our data, the length of the track was 103 centimeters, the height from track to table was 74 centimeters, and the distance from ground to end of ramp was 72 centimeters. The mass of car number 1 was 45 grams, and the mass of car number 2 was 34 grams. The height at the top and bottom positions respectively was 0.788 meters and 0.492 meters, and the difference in height was 0.296 meters.
Trail 1, 3, 2, 1, go. Trail 2, 3, 2, 1, go. Trail 3, 3, 2, 1, go.
As shown in the graphs, our observed final velocity was 2.13 meters per second, compared to our predicted final velocity 2.4 meters per second. This leaves us with a percent error of 12.7%. In conclusion, we found that acceleration, force, and mass are not considered when the ramp is curved. We also found that the determination of final velocity is necessary to demonstrate the conservation of energy in Newton's second law of motion. Also, the predicted final velocity was compared with the observed horizontal and vertical velocities. At the end, the percent error was found to be low. If less experimental error, it would be even more clear that energy is conserved in this experimental system.